I'm Ayusha and today I'll be discussing few topics before you. So let's start with moment of inertia matrix. Consider rigid body rotating with fixed angular velocity omega about an axis which passes through the origin. Let Ri be the position vector of the ith mass element whose mass is mi. We expect this position vector to precess about the axis of rotation with angular velocity omega. It therefore follows from equation that dRi by dt is equal to omega cross Ri. Thus the above equation specifies that Vi is equal to dRi by dt of each element as the body rotates with fixed angular velocity omega about an axis passing through the origin. The total angular momentum of the body about the origin is written as L is equal to sigma of mi cross mi Ri cross dRi by dt is equal to sigma of mi Ri cross omega cross Ri is equal to sigma of mi Ri square omega minus Ri omega Ri, where use has been made of equation previously discussed and some vector identities. The above formula can be written as a metric equation of the form Ix, Iy, Iz. This is your LHS and RHS is Ixx, Ixy, Iyz, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, Izz, omega x, omega y, omega z, where your Ixx is integration of y square plus z square dm, Iyy is x square plus z square dm, and similar pattern follows for Izz also. Also, Ixy is equal to Iyx and that is equal to minus of xy dm. Iyz is equal to minus Izy is equal to minus of yz, this is dm, sorry, yz dm, and similar pattern follows for Izz also. So this quantity here is called moment of inertia matrix. In mathematics, the Hermite polynomials are a classical orthogonal polynomial sequence. Basically, there are two different ways of standardizing the Hermite polynomials. The first one is probabilist Hermite polynomials. They are represented by HE and are written as Hen of x is equal to minus 1 power n e power x square by 2 dm by dxn e power minus x square by 2 is equal to x minus d by dx of n dot 1. While the second type of polynomial is physicist Hermite polynomial, and they are represented by a simple h and are expressed as Hn of x is equal to minus 1 power n e x square dm upon dxn e minus x square is equal to 2x minus d by dx of n dot 1. These two definitions are not exactly identical. Each one is a rescaling of the other. That is, Hn of x is equal to 2 n by power n by 2 he of n root 2 x. So basically we are seeing one in terms of another. These are Hermite polynomial sequences of different variances. The first, some of the first probabilist Hermite polynomials are he of 0 of x equal to 1, he of 1 of x equal to x, he of 2 of x is equal to x square minus 1, and so on. And some of the first Physis Hermite polynomials are h naught h0 of x equal to 1, sorry, h1 of x equal to 2x, h2 of x equal to 4x square minus 2, and so on. As we discussed before that they are orthogonal polynomial sequence. So let's now talk about their orthogonality. Hn of x and hen of x are n degree polynomials for n equal to 0, 1, 2, 3, and so on. These polynomials are orthogonal with respect to the weight function w of x equal to e power minus x square by 2, or you can say w of x equal to e power minus x square. This one is for he and this one is for h. That is, we have integration from minus infinity to infinity of hn of x w of x dot dx equal to 0, where m not equal to n. Furthermore, integration of minus infinity to infinity of he of m of x hen of x e power minus x square by 2 dot dx equal to root 2 pi n factorial into delta of mn. So let's move on to our next topic, that are Laguerre polynomials. In mathematics, the Laguerre polynomials named after Edmund Laguerre are solutions of Laguerre's equation xy double dash plus 1 minus x y dash plus ny equal to 0, which is a second order linear differential equation. This equation has non-singular solutions only if n is a non-negative integer. More generally, the name Laguerre polynomials is used for solutions of xy double dash plus alpha plus 1 minus xy dash plus ny equal to 0. Then they are also named generalized Laguerre polynomials, as will be done here. The Laguerre polynomials are also used for Gaussian quadrature to numerically compute integrals of the form 0 to infinity f of x e power minus x dx. These polynomials, usually denoted as L0, L1, and so on, are a polynomial sequence which may be defined by Rodriguez formula. That is, ln of x is equal to e power x upon n factorial dm of dxn of e power minus go. So I have written it down completely. I'll repeat it. Ln of x is equal to e power x upon n factorial into df of dxn into e power minus x dot x power n is equal to 1 upon n factorial d by dx minus 1 of n x power n, reducing to the closed form of a following section. These are orthogonal polynomials with respect to an inner product. We can write it as fg is equal to 0 to infinity f of x g of x into e power minus x dot dx. The sequence of a Laguerre polynomials n factorial. Ln is a Sheffer sequence. We can write it as d by dx of ln is equal to d by dx minus 1 of ln minus 1. This is the relation between ln and ln minus 1. So let's look at first few polynomials of Laguerre series. For n equal to 0, Laguerre polynomial is represented as 1 is 1, L1 is minus x plus 1, L2 is x square minus 4x plus 2 upon 2, L3 is minus x cube plus 9x square minus 18x plus 6 upon 6, and so on. So this was Laguerre's polynomial. Now we'll move on to the topic of rocket dynamics. So we'll try to understand rocket dynamics using Hamilton's and Lagrange equations. Consider a rocket of variable mass m moving with velocity v. Then its total energy can be given as half mv square minus v of q. By Euler's Lagrange equation, we already know that d by dt of del L by del Q dot minus del L by del Q is equal to 0. So using the previous equation that we wrote just here, d by dt of mv plus delta v is equal to 0. So normally it will turn out to be d by dt of mv is equal to minus delta v. By principle of least section, we know that change in integration of L of q dot q comma q dot is equal to 0. Now section, we have shown that Hamilton's principle is equivalent to Euler-Lagrange equation. In the case of external forces, Fxt is equal, we modify Hamilton's principle to the Lagrange D'Alembert principle. That is delta of L q comma q dot dt plus F external dot delta q dt is equal to 0, where F external are the external forces. Note that forces that come from a potential are conventionally put into Lagrangian. Hence, by external we mean forces that are not derived from potential, such as friction or the propulsion force of a rocket in this case. However, if potential forces were to be included as external forces, then the system remains consistent. The same argument that uses to show that Hamilton's principle is equivalent to the Euler-Lagrange equations shows that Lagrange-D'Alembert principle is equivalent to Euler-Lagrange equations with external forces. So, d by dt of del L by del Q dot minus del L by del Q is equal to F external Q comma Q dot. For instance, in the rocket example, the final equation will look like d by dt of mq dot is equal to minus delta v plus F external. There are correct equations when these are correct equations when the mass of the rocket is allowed to change with time. Note that one cannot just pull the m out of derivative sign, as one might guess if one naively uses F equal to ma. So this is our final equation here when we consider the external forces acting on the rocket that are propulsion. That is its propulsion. Thank you and have a nice day.